download. Everything looks good. So Mehdi is from University of Toronto on speaking about a deep learning algorithm for piecewise linear interface construction. It's all yours.
Okay, thank you very much for introduction. Today I'm going to introduce a deep learning algorithm that can directly solve the piecewise linear interface construction. So first I want to introduce what is this problem that we want to solve. So imagine that we have a cube and a plane, and the plane intersects the cube. So because of this intersection, a polyhedron forms below the plane. So the problem of piecewise linear interface construction, or in short, PELIC, I'm going to call it PELIC from now on, is that if the volume of this polyhedron is given to you, and also the normal of this plane, what is the constancy of the plane? So basically, I want to repeat that we give the volume of this polyhedron that is formed under this plane. We have the normal, and the goal is to find this constant C. So basically, the location of this plane relative to the origin. So it looks like a very simple geometrical problem, but it's actually not. It's a very complex geometrical problem, and it has been studied for 20 years. So this is a problem, but I want to first talk about why we're even interested in solving this problem. So in CFD, computational fluid dynamics of modeling of multi-phase flows, when we have multiple phases like gas and liquid interacting with each other, there is a technique called volume of fluid method to track the location of the interface between these two phases. The example that I'm showing here is a gas bubble inside a liquid. So the volume of fluid method assigns a scalar field, here we call it alpha, to the phases, and it takes a value between 0 and 1. For example, it takes a value of 0 when the phase is gas, and it takes a value of 1 when the phase is liquid. And whenever we have an interface, it takes a value between 0 and 1. So in this example, you can see red is 1, blue is 0. So we have gas here, and the interface is shown with any value between 0 and 1. So you can imagine that when we have this scalar field, which represents the interface, if I solve an advection equation based on the velocity field that I have, I should be able to track the location of the interface throughout the simulation. Also, this alpha I want to add is that it's also used when calculating the properties of the liquid that we have, of the fluid that we have in each cell. So it's usually there are different techniques. For example, they varied by the alpha of that phase. So this alpha is used to track the interface and also calculate the properties of the fluid in each interface cell. So it looks very simple. We solve this. We're good. But the issue is that solving this advection equation for alpha is a little bit challenging, and that's usually because alpha is discontinuous. It jumps from 0 and 1 at the interface. And because of that, it can create a lot of smearing, as the example that I'm showing on the bottom. Let me choose a laser pointer. So you can see what we like is a sharp interface, but because of that smearing, we might end up with something like this, which doesn't represent an interface that we like. And you don't see interfaces in practice. If you I don't know, see a river, the interface doesn't look like this. If it's not, if there is no condensation or any other type of phenomenon happening here. So normally it's very sharp. So there are different techniques that has been developed to discretize this divergence term that we have in a way that is efficient and effective for interface construction. They're called donor acceptor comparison methods, NVD. So all of these trying to discretize the convection term using higher order methods or normalization techniques to fix this smearing problem. There's another class of solutions that are used to circumvent this issue with this discretization, and there are geometrical techniques. In these geometrical techniques, the interface is approximated. For example, the simplest method is called simple line interface calculation. So basically, you approximate the interface with a line parallel to one of our coordinates, depending on the direction of the normal. And we put this line where the volume on their volume or area into the under this line is equal to alpha that we have. So we approximate it this way, which is the first order approximation. There's another technique, which comes back to what we were talking about, is piecewise linear interface construction. And as you can see here, we approximate interface with lines instead of this line like this. And you can imagine that this is a better approximation, and it's a second order method. So how this circumvent the discretization problem? So when you have a very accurate reconstruction of the interface, this process is called reconstruction. You can calculate the fluxes between different cells, and based on those fluxes, you can actually calculate the convection term instead of using a high order method, for example. So, and there's also other use cases for the reconstruction. This is a work of in my PhD. I studied foaming phenomena in CFD. So there's a lot of bubbles interacting with each other. So there is a force between these bubbles. It's called disjoining pressure that needs to be calculated. And this force is a function of a distance between the interface of two adjacent bubbles. So you need the reconstruction techniques to calculate the distance and in order to calculate the disjoining pressure between different bubbles. So it's not only for tracking alpha, it has other applications in CFD simulations as well. So in order to formalize the problem that we're talking about, given an interface normal n and the volume fraction alpha, our goal is to find C, the constant C of this plane. Like this example here, for the same bubble, the interface will be something like this, where the alpha below it, for example, for a cell here, we have the normal, and we want to place a plane in the correct location that the volume underneath is alpha. And this normal is calculated in different techniques. Using different techniques, the simplest one is just using the gradient. You can find a normal to this interface. So that's how we get the normal here. So in this discussion, we call this a forward problem of PELIC, which is also used in the literature as well. So we have alpha, we have n. Our goal is to find C, and this is a forward problem of PELIC. So it's good to remember this because we come back to this forward problem. So as I explained, this is a very complex, it can be complex because there is sophisticated operations involved in calculating the C. You have to deal with inverse of third degree polynomials, and complex numbers show up, and when they show up, you have to eliminate them, and computers are very good in very optimized in calculating complex number operations. And the solutions are segmented. For example, depending on where you place that plane, the polyhedron shape changes. If I go back for 1 second to show you this example, the shape of the polyhedron is different. They have different number of faces. So that means that the solution to the PELIC will be segmented. And there have been different techniques have been developed throughout the years to solve PELIC, analytical techniques, iterative techniques, and approximation techniques to make it faster. It's a very slow process because of the problems that I just mentioned here. So in this, we have published a previous work to use neural network to solve this problem. So we generated a synthetic data set of PELIC solutions using available techniques. We normalized the meshes that we were dealing with to reduce the number of parameters to this neural network, and we were actually able to get good results out of this technique, which we called it NPELIC. However, this technique had a few limitations. It required preparing a synthetic data set of PELIC solutions for different alpha, different normals. until you have to access to a PELIC solver. And it's also the accuracy is always limited to the accuracy of the data set that you have. You can never exceed them or propose a better method. So the accuracy is limited, and you have to have access to a PELIC solver in order to generate the data set. So we wanted to use the inverse problem inverse problem of PELIC and use a neural network to solve the problems. Why we wanted to use the inverse problem is because, unlike the forward problem, this inverse problem is very simple. What is the inverse problem of PELIC is that instead of asking you to find the location, the value of C of that plane, they give you the C, they give you the normal, and then they ask you to find the alpha, which is basically the volume of that polyhedron formed by the intersection of the given plane. So I don't want you to see calculate C. I want you to calculate alpha, which is a very simple geometrical problem, and we call this the inverse problem of PELIC because we flip the alpha and C in this set of equations. So why this is simple? Why the inverse problem is simple, unlike the forward problem? First, if you remove all the symmetrical cases, there will be only 5 possible cases for intersection of a plane and a unit cube, which are all shown here to you. So very simple, and so there are not too many cases that we have to deal with. There's only 5. Second is that calculating the volume of this polyhedron is a middle school, high school geometry problem. All you need to do is to calculate the volume of this pyramid here and subtract the parts that extend beyond this cube. So I calculate this the volume of this pyramid, I subtract these two, and I'm done. So it's a very simple problem. It's not like the forward problem. So you can calculate all the equations for all different the 5 cases that I showed you. It's based on the M, which is simply the components of the normal along the 3 axes that we show here. We have to do a coordinate transformation because we normalize all the cases to just those 5 intersection sets. And D, which is the smallest distance from the plane the small distance from the plane to the origin, which is equivalent to the C that we were calculating before. You can easily linearly map them to each other. So based on D, you have D. D is given to you in the inverse problem. You come here and find the correct equation and solve and get V. But in the backwards problem, you don't know D, so you don't know which equation to use, actually. So you have to go back and forth. If you choose D wrong, you have to iterate through them and figure out what the correct solution is. So yeah, so this is the technique to solve the inverse problem, which is a simple geometrical problem. Now the idea is that how we can basically utilize this simple inverse problem to solve the forward problem directly. What we did was that we convert this PELIC problem into an optimization problem that a neural network can solve. And we define this loss function that is simply the difference between the real volume underneath the plane and alpha, which was given to the neural network. So this loss function, we are able to calculate this loss function for a neural network because this V is given by the inverse problem, and it's a simple problem, and we have the analytical solution for it. And alpha is known in the forward problem. So we don't have any issues calculating this loss function for a neural network. So that's what we wanted to leverage in this work. So the goal is to find D, the output of this neural network, such that the volume of V of the truncated polyhedron that we have to be equal to alpha. So you can imagine if this loss function goes to 0, we have solved the forward problem of PELIC. So in order to illustrate that a bit better, here you can see a neural network, the neural network system that we have. So the inputs are M1, M2, M3, which are the components of our normal on the coordinates, and alpha. We give it to the neural network. We calculate D, which is equal to the C constant that we talked before. And then you get D, calculate this loss function. We have the alpha from the input. We have V from the analytical solution from the inverse problem. we can calculate the loss function, and we can optimize. We can just keep training this neural network until this loss function on our validation set is less than a certain value. Or we can just, as much as the resources that we have, we can just keep training it and hope that it would become more and more accurate. So in those four, we use a fully convoluted neural network, MLP neural network, with 1 or 2 hidden layers. And each hidden layer had 24 or 48 neurons, which we found to be enough to solve this problem accurately. So the training went very well. The neural network was able to actually solve this, solve the for-our problem. We use different randomizers to make sure that the results are reproducible, and we sample the space of the normals and alpha uniformly to make sure that we sample the spaces of the normals of our input parameters in an efficient way. Basically, this training doesn't take that much time, so we kept running it for 12 epochs to see how accurate it gets. This was kind of like we just played around with it, and we found that it wasn't really necessary to keep going after that. So as you can see here on the left, I'm showing the alpha predicted by the neural network and the alpha that we give it as for the input. So this alpha predicted is calculated using the inverse problem. So we take the D outside of the neural network. We use the inverse problem to find what's the actual alpha that is being predicted. And this is the alpha real which was given to the neural network. And in an ideal scenario, everything lies on the diagonal. So as you can see, the prediction of neural network was very accurate. Here I'm also showing you the mean squared error and the max absolute error for different number of neurons in the hidden layers, and also different number of hidden layers. And as expected, when we increased the number of hidden layers, the accuracy increased, but not so much. So you can actually get away with a lower number of neurons, because some of the approximation methods that have been developed in the literature, they have even lower mean squared error than this technique. So we are good in terms of the error. So and one benefit that you can only imagine that we would have here is the speed up the gain that we get. So we compare it to an analytical technique, which is a very fast technique that is often used in the literature. And since we're using a neural network, we can actually parallelize it on CPU and GPU. So, but we didn't have the GPU implementation of the analytical solution. So we used the analytical PELIC on one CPU core as our baseline, and using that baseline, the neural network could be up to 41 times faster when on GPU, and 3 times faster on one CPU core. And so we ran it for different number of cells. As you can see, when we increase the number of cells, the speed up increases, and that's because the neural network is able to calculate all of these PELICs for all the cells in batches. So yeah, we investigated why we observed this speed up. In our earlier work in PELIC, because at the end we get the neural network that can solve PELIC, we investigated this and we found out that although the neural network operation, the DNA and the neural network that we have requires more floating point operations to solve the PELIC, it utilizes the hardware much better. So it operates at a very higher floating point operations per second. And that's because there is a lot of if statements here and there. There is no solving inverse problem of third-degree polynomials there. It's just simply a matrix multiplication. And also another reason for the speed up is that PELIC can do the calculation in batches, which is not possible using conventional techniques. So as I mentioned, the method can be faster. You don't need any knowledge of any PELIC solutions. So the neural network solve the PELIC directly. You don't need to know any, you don't need to be aware of any of the available solutions. It's very portable. You can imagine that you can just move the weights around to any program that you want and do the calculations, and it's parallelizable, unlike the traditional models on CPU and GPU. And also the runtime, the overhead runtime that it has on your simulation is constant because the calculations are constant and it's very predictable. And this is not the case when you use traditional techniques, and because in some cases the calculation is very simple and they're fast, and in some cases you have to do a lot of iterations and back and forth to do the correct calculations, and the overhead changes depending on the location of the interface and the value of alpha. So, but using this technique is predictable and constant. So these are the advantages of using a neural network instead of a traditional algorithm. So yeah, thank you very much. I hope that